Hello and a very warm welcome on behalf of NTI Audio. Today we want to introduce you how to test digital MEMS microphones. But first let me please introduce myself. My name is Markus Becker and I'm assisted today by Greg Schmiedle, our product manager. He will especially take care of your inputs during the presentation. The topics that we have prepared for this webinar start with a brief overlook on MEMS microphones, followed by an introduction to a typical test setup and some explanations about the communication interface between MEMS microphones and the signal processor. We will also clarify some important terms and parameters that are related to MEMS microphones and make some statements on the MEMS mic interface box, which plays a key role in this test. We have also prepared a practical presentation for you, which will be followed by an overview on the hardware and software that you need and some additional hints and tips. At the very end, I will come back to the questions that have popped in and possibly provide some additional information. I expect that the whole webinar will last about half an hour. But first, let us take a look on the definition of a MEMS microphone. MEMS stands for microelectromechanical system. So these are typically devices that are designed and built in silicon chips. They can be analog or digital. In this webinar, we are explicitly referring to digital MEMS microphones. Well, the advantage of implementing these devices on a silicon chip are the low production costs. So consequently, typically we have a couple of MEMS microphones per device due to the low costs. The devices where you can find MEMS microphones nowadays are mobile phones. You can find them in cars, but also in smart devices and many more similar items. Please keep in mind that MEMS microphones are very frequently placed in an array structure on the item in which they are built in. This array structure allows the so-called beamforming and noise cancellation. How does that work? Let us take a look at this example of a MEMS microphone array of 6 microphones. You see these black ones here. Now, if we have a person in the room who is talking, we will notice that the time it takes from the sound from the speaker's mouth to the corresponding microphones varies. And these time variations or delays can be calculated and reconstructed by a processor in terms that it is possible to identify the direction from where the sound is coming from. So you can focus on a single speaker, a single sound source in the room. And in addition, having done that, you can cancel the ambient noise that has been created somewhere around. So this is a huge advantage of an array of MEMS microphones. One more side information to which I will come back later is that a prerequisite of this procedure, of this technology of beamforming, is that these MEMS microphones on the array are behaving very similarly. So each of these microphones should have a comparable, a similar sensitivity so that it translates the incoming sound in almost the same way as the neighboring microphones. But as stated before, I will come back to this issue later. How does a typical test setup look like? First, we should place our device under test in a homogeneous sound field. And for that purpose, we recommend to use a single high-quality loudspeaker that is located on axis to the device under test. The test signal itself is typically a glide sweep, which has a couple of advantages. It allows a pretty fast test. It allows to measure several parameters in parallel, like frequency response or distortion and other results. So this is a very popular test signal for this setup. We also need a precision reference microphone for two reasons. The first one is when we want to determine the frequency response of these MEMS microphones, we have to compare them against a known reference, and that would be our precision microphone. And the second reason is that when we want to calibrate our system, in order to make sure that the sound pressure level coming from this loudspeaker, arriving here at the device under test, that this sound pressure level has a certain value, we need a reference microphone with a known sensitivity in order to calibrate the system. Well, the next step is that the digital signals from these MEMS microphones will be transferred to the MEMS mic interface box, which converts them into analog signals, and these analog signals will be then forwarded to a multi-channel audio analyzer that calculates the required test results. Now let us take a closer look on the communication between MEMS microphone and the DSP, the digital signal processor. This communication interface is typically established by using a half-cycle PDM interface. And this looks like that. We have here two MEMS microphones, one for the left channel and one for the right channel. Both are connected in parallel via two lines to the DSP, the digital signal processor. The first line is a clock line that comes from the DSP and drives the two microphones. And the other line is the feedback line. So through this connection, the data stream from the first and the second microphone are fed into the DSP. Now, how does that look like in detail? Well, the standard defines that by the rising edge of the clock signal, the following data bit represents data from the left microphone. And the data bit that follows on a falling edge of the clock signal represents data from the right microphone. So by this pattern, you may transmit left mic data and right mic data via one joint signal line. But what happens if one of these microphones is missing or is faulty? Well, in that case, we would face the following situation. We would have data from the correctly working right microphone, and the following bit, which should come from the left one, would just be mirrored. So it would be the same data as from this bit. Here we have the next bit, and that would be again the same, the next bit, and the same. So the problem here is that the DSP needs a way to differentiate whether this is really the identical data from another microphone or whether it is, like in this case, the same data as from the right microphone because the left one is faulty. Well, the good news is that our MEMS mic interface box is able to detect such a situation. It is able to detect a missing or faulty microphone and to alert the user accordingly. Here are some other important terms and parameters that are related to MEMS mic testing. First of all, we have the EIN, the equivalent input noise. If we translate that into the analog world, like on this schematic picture, that would correspond to the residual noise of the MEMS microphone. So the inherent noise that is somehow created by the MEMS microphone corresponds to this EIN level. The next one would be the AOP, the acoustic overload point. And that level represents the maximum level that the microphone still can convert into a digital signal without clipping. Typically, depending on the MEMS mic type, this AOP would correspond to a sound pressure level of approximately 120 dB SPL. What is important that these AOP point also defines the 0 dBFS reference. dBFS stands for decibel full scale. So the AOP point always defines the 0 dBFS reference point for the digital level scale. I will show you that on the next slide again. And the third important parameter is the sensitivity of the microphone. And that is defined as the difference between the AOP and the level that would correspond to a 94 dB SPL sound pressure level. You see here the difference between these two levels, AOP minus the calibrator level. The calibrator level of 94 dB SPL is a typical standardized level that allows us to define this microphone sensitivity. Now let us take a look at this whole situation from a different angle. Here we have the analog sound pressure level scale, and on the right hand side the corresponding digital MEMS output scale. So the AOP, the acoustic overload point, for instance at 100 dB SPL, gives us the 0 dBFS. The EIN, the noise floor, which in this case would correspond to about 30 dB SPL, would be in this case at minus 90 dBFS. When we look at the dynamic range, that is the difference between this EIN and the AOP. In our example, this is 90 dB. The sensitivity, as stated before, is the level which corresponds to 94 dB SPL. In our example, this would be minus 26 dBFS. So that is the sensitivity of this particular MEMS microphone. Then we have the signal to noise ratio, and that is for MEMS microphones defined as the difference between the sensitivity and the EIN. Last but not least, we have to deal with a very important parameter which is called the sensitivity span of a MEMS mic array. And this is defined as the difference between the lowest and the highest sensitivity of all MEMS microphones on that array. Maybe you remember what I said in the very beginning of this presentation, that it is important for beamforming that the MEMS mics on your array behave as similar as possible. The characteristics should be as close to each other as possible to allow the DSP to properly calculate the source, the direction of the sound source. So we need to know this sensitivity span, this difference between the microphone with the lowest and the microphone with the highest sensitivity on our array. Let me go a little bit deeper into this topic. You remember the definition of the MEMS mic sensitivity was the AOP minus calibration level. So within a production batch, you typically have similar sensitivities of the MEMS microphones. However, when you place them on a substrate like you can see here, a widespread, it's not a symmetric substrate, or the array is not symmetric, you have different distances from these MEMS microphones to our test signal source. And it is quite apparent that, for instance, this microphone here or that one, they will receive a lower sound pressure level compared to the ones in the middle. And that gives us the problem that the measured sensitivity varies from the actual sensitivity of these microphones. So we have to overcome this problem, and we do that by adding individual offsets to the measured sensitivities, depending on the position where the MEMS microphone is. And that allows us to calculate the true actual sensitivity of each microphone. Giving you an example, here we have MEMS microphone number 1, and we can determine that we need to add an offset of 1.5 dB to the measured sensitivity, and that will give us the true sensitivity of the microphone. Now we do the same for the other microphones. Here for the number 2, we have a slightly lower offset, 1 dB, Number 3 does not need any offset because it's quite in the front of the test signal source anyway. Offset for number 4 is a little bit higher, 0.2, and for number 5 is in the range of 1.3. So by adding these individual offsets, we are able to determine the true sensitivities of the microphones, and that allows us to correctly calculate the sensitivity span of our microphone array, regardless how the test setup looks like. Some words about the MEMS MIG interface test box. It has 2 supply voltages, the typical ones, 1.8 volt or 3.3 volt, selectable. We have 4 selectable clock frequencies. Keep in mind, the higher the clock frequency, the higher the power consumption of the MEMS microphone, but also the better the audio quality. The MEMS interface box translates the digital signals into an analog voltage, which is maximum 3 volt. And now we have to calibrate this whole setup. When you are used to work with conventional microphones, you know we have a microphone calibrator which you can plug on the microphone, and then you measure the output signal, the output voltage, and in this way you can determine the sensitivity and so forth. With a MEMS microphone, this is not possible because they are too small. You cannot plug them into a microphone calibrator, so we need a different approach to calibrate the system. So what we do is we send a command to the microphone interface box, which corresponds to a 0 dBFS full-scale signal, and the microphone interface box translates that into the voltage, for instance 4.9 dB volt. And this voltage, corresponding to the 0 dBFS, can be measured by our test instrument, and this way we can calibrate the whole system. So this brings us to our practical presentation. I have here on my desk an FX100 audio analyzer, a MEMS MIG interface box. I have a reference loudspeaker with microphone, MEMS microphone and reference microphone, and a controller PC with the Artemic FX software. I'm gonna switch over to that, but before I just want to add a video webcam so that you can also watch the setup here on my desk. Here you see the reference loudspeaker. This is the MEMS microphone, and in the middle we have the reference microphone. This is the MEMS MIG interface box, and here on the right hand side we have the FX100 analyzer. Now let us take a look at the setup in the software. The first thing we have to do, we have to verify the basic configuration. And here it is important to have the reference microphone activated. That has already been done. You see it here. And also to connect a digital MEMS MIG box to the system. That has also already been done. I could test the connection, but I know it's working fine, so I leave it as it is. Next step is to add a project, to create a new project. We can label it the way we want, and we select the project type. In that case, it would be Digital MEMS MIG project. Well, I have already done that, so I just cancel here, but I will now show you the parameters of this predefined test project. We have one device under test. We are using an internal input switcher, internally within the FX100. As we have 4 MEMS MIGs on our device under test, we will do that in 4 cycles. And we are using the 2.5 megahertz, and we have selected a grouping mode of 4 times 2 microphones. Here you can see the measurement functions that we have activated, the frequency response, distortion, sensitivity and sensitivity span. Please notice that we are sharing the test signal from the frequency response test with the distortion test. So these 2 measurements will be executed just in parallel, together with the other, by the way. Now let us take a look at the definition of this test signal. We have a bandwidth from 100 Hertz to 10 kilohertz, which is quite typical for MEMS mix. Then let's take a look at the sensitivity. We are testing the sensitivity at 1 kilohertz. Here we have the definition for the sensitivity span. So here you can see the 4 values for the 4 MEMS microphones, 0.7 to 1.5. So this is the compensation of the test setup imperfectness, if you want to say that. So these are the individual compensations that will in the end result in a very close, very small sensitivity span. Last but not least, here the distortion definition. I'm actually restricting myself to a measurement at 1 kilohertz, distortion measurement at 1 kilohertz. You will see that in a minute. So the next step is to calibrate the system. And for that purpose, I have to make sure that I have connected the reference microphone to, in that case, input channel 2, and I start the calibration procedure. I hope you could hear the test signal that was used. That is the glide sweep. I close that. And now the next step is to take the references. Actually, when you want to implement a production test, you always need to know what is good, what is bad. So where are the tolerance limits? And for that purpose, you usually use a golden sample or maybe several golden samples. So MEMS microphones from which you know they are behaving properly. And you record the behavior of these reference microphones and compare all further microphones in your production with these golden samples. So I'm going to show you the recording of this reference microphone, of this golden sample. You remember we had 4 microphones and 4 cycles. You heard them, and each of these 4 microphones has its own frequency response that you can watch here on the left-hand side, has its own distortion response. The green, fat green line represents the average of the 4 samples. So we close, and now we are ready to enter the production mode, the passed-failed test. Now, in my example, I just leave the microphone as it is. I don't replace it with another one. And you see here this green area, that's the tolerance band. So all measurements that are within that band are passed. The same applies here for the sensitivity, which must be between these 2 values. Down here, we will see the acceptance limit for the distortion and for the sensitivity span. I'm just starting the procedure, and you can see by yourself how it works. Again, 4 cycles, 1 for each microphone. All curves are within the band. The sensitivity is within the limits. The tolerances, you can see that slightly down here, is also within limits. And the sensitivity span is also below the defined limit. Well, that is basically the practical presentation. So let me get back to my PowerPoint presentation and summarize the hardware and software that we have been using. We have here an FX100 analyzer rear view. This is a modular instrument, so you may decide whether you want to buy it with 2 channel input-output channels or with 4. This example here has 4 channels. You can see that here each of these channels has 2 connectors, an XLR and a BNC. So that would allow you to connect up to 6 microphones directly to the inputs of the test instrument. The last input channel is reserved for the reference microphone. Alternatively, you can also plug in an input switcher, 4-channel input switcher. This will allow you to sequentially test these MEMS microphones as you have seen that in our example just a couple of minutes ago. The software that we are using controls both the analyzer and the MEMS mic interface box. Alternatively, we have also another software. It's called the MEMS box control software, free of charge, available from us. It's a very simple, basically it's just a user interface which allows you to address this MEMS interface box to see how many microphones have been connected. This is mainly intended for lab use or if you want to write your own control software for the test. Last but not least, we need the reference microphone and the remote controlled loudspeaker for our test setup. One more slide on the MEMS mic interface box. Keep in mind, this box from NTI Audio is able to detect missing or faulty MEMS microphones. It can handle up to 8 mono microphones or 4x2 MEMS mics. And we have 2 connectors here for 4 mics each, and we can toggle between these 2 connectors if we like. Keep in mind when you connect the box to MEMS mics to keep the connecting cable short in order to avoid data loss or any other kind of problems. So this is something that you should keep in mind. And also, as stated before, the higher the clock frequency, the higher is the power consumption of your MEMS mix, but also the audio quality. That is up to your decision in which range you want to work. Well, I'm at the end of my presentation. From my side, I want to thank you very much for your attention. I hope I was able to answer most of your questions, and I would of course be happy to welcome you again at one of our future webinars, for which you will receive an invitation as usual. So thank you very much for your attention and have a good day. Thank you very much. Bye-bye.